All right. So I just got this pop up here. It's not due for a while. But that next homework I've got up on Canvas now. As we work through more material, you'll be able to kind of chip away at this. I think right now you wouldn't be able to get through maybe 4 or 5 questions after today, maybe another 4 more. But there's, I think, 21 questions on it. Or no, sorry, I added a bunch. This one has 30 questions. That's why the due date's kind of quite a ways off in the future. But I would kind of highly suggest working on those game theory ones, like the first 10 questions, which will be stuff we covered last week and then today. That way, wait until the day before it's due. That's going to be quite a ways in the past. We talked about this stuff. Okay. So that's up there right now. Everything else should kind of be factored into your grade. Once again, those exam scores are up there. Already had to have the curve built into them. So your grade on Canvas should give you, an accurate idea of where you're currently at in the class. Okay. Any questions from me before we kind of get started here? Okay. So I think what we're going to do is work through the rest of this game theory, maybe start talking about externalities today. And then Friday, we'll do a little bit of material, but I'll probably also work through some of the questions on that practice problem 4 file that I have up, practice problem 5, sorry. File that's up on Canvas that has kind of a set of questions related to kind of what we're going to be covering. But I just want to kind of start maybe at the end of each week, kind of going through a few of those questions in kind of the second half of the class, hopefully kind of preparing us for that final. Okay. So trying something new here. I guess you guys are my guinea pig, but or guinea pigs. So, all right. So where we leave off, we're talking about game theory. I showed you some, how we would look at oligopoly models. We looked at some pretty goofy models, but we kind of talked about identifying Nash equilibrium. Right? So we still want to be able to do that. And what we're going to do today is identify what the equilibrium or Nash equilibrium is, or what's the outcome where both parties are best responding to what the other person is doing. The only difference is for extensive form games, we're modeling these games that don't have simultaneous decisions, which we use those payoff matrices for, but they're actually going to have sequential decisions, right? One person does something, and then the other person can respond. Right? That's sort of what the other person did and then respond. So what we're going to kind of write this out is like a decision tree, or decision tree, right? We're going to have the first person, right? Just kind of like we were doing before. We got player 1. This could be firms, this could be countries, this could be just people. They're then going to have strategy choices. They could have more than 2, but I'm just modeling this one to kind of introduce it. It'd be pretty easy. They could choose either A or B. Right? And then player 2 sees that decision and has their own response to make. So maybe player 2 can choose either option C or D under both scenarios, right? So player 2 has their strategies. Here's player 1's strategies. And then at the end here, we would write out what their payoffs are. So we would kind of write the payoff to player 1, and then the payoff to player 2, payoff to player 1, comma, payoff player 2, and the same thing on the other side, right? This will look a little bit more interesting once we have some actual values to put to this, but this is the general form of what we're going to be doing, right? So before, we kind of had this matrix where we had the strategies as like our column and row labels, and then the payoffs were in the middle. Now, kind of these arrows, the parts of our decision tree, are going to represent the strategies and the players deciding between those strategies. And then the last row, right, or where the arrow ends, then we'll write our payoffs there. Now, we're going to solve these a little bit differently, but this is what they're going to look like. So I've got a pretty basic one here, and kind of an age-old example. But we're also going to think about how do we solve these. And so the way we solve these is what we call backward induction. Because player 1 is making their choice first, right? They know that player 2 is always just going to best respond to that. But if player one knows player two's payoffs, and that's what we're going to start out assuming, right? These models get complicated if we don't, but for now, we'll say we know the payoffs from the combinations of strategies of player one and player two. Both players know those. So I know that I can figure out what player two's best responses are to what I do. And then because I know their best response, I know kind of which part of the tree I'm going to end up with or end up at on either side. I'll then make my best response to what I know the other person's going to do. So I'll kind of walk through this next example here. So let's say we've got Charlie Brown, right? He either accept or reject to play this game with Lucy, right? The game is that he runs at a football and she either lets him kick the football or pulls it away at the last second, right? And he knows this because this always happens, right? These are her two strategies. If she lets him kick the ball, he kicks the football, Lucy's not amused at all. If she pulls it away, he falls down, and she's very amused. Now, if we put some values here, maybe her being amused is positive 10, not being amused negative 10, right? So we know that if Charlie Brown accepts this game, what will Lucy always do? Well, if we look at her payoff, she's always would rather be amused than not amused. So we know that this is going to be her best response to Charlie Brown accepting the game, right? So she's going to pull the football away. That's always her best response. So we're using backward induction where we're starting with the second decision maker, right? The second player. Charlie Brown first decides to either accept or reject this game, and then Lucy makes the decision to either pull the ball away or keep it there. Right? So Charlie Brown looks at this and says, look, if I accept this game, I know that Lucy's always going to choose to pull the football away. And I fall, right? So if I reject to play this game, nothing happens, right? I don't have this negative consequence or payoff. What's better for me? Well, for nothing to happen as opposed to me falling down. And so his best response is then to reject this game. Okay. Now, this one I made a little bit easier by kind of shutting down, like if he rejects the game, Lucy doesn't have a decision to make, right? But that's the idea. We'll start with a second person, figure out what their best response is to what the player one is doing, and then player one knows what those are and decides what's the best for them. Okay. So let's go through one more and we kind of talk maybe a little bit more about this, but I think seeing this example. So let's say I've got more of a kind of monopoly example, and I'm thinking about whether or not firms want to enter this market. Okay. So I've got my existing monopoly, and they're going to set a price. Okay. So they're going to either set this higher monopoly price, or they're going to set a more competitive price closer to that perfectly competitive kind of what we would see that perfectly competitive price. There's another firm deciding whether or not, after they see the price that the monopoly sets, do they enter or stay out of this market. Okay. So you can kind of think about, well, if they're setting the monopoly sets the price pretty high, some firms might see that and be like, oh, there's some profits to be made there, right? That price is above my average total cost, so I want to get into that industry. But if the monopoly keeps the price a little bit lower, well, maybe then other firms will be like, yeah, that price isn't quite larger than my average total cost. I don't want to enter, right? And then they kind of remain a monopoly. So if they keep that higher monopoly price, targeting higher profits, if that firm who's thinking about whether or not they want to enter, if they stay out, well, then they're still a monopolist. They enjoy positive monopoly profits. The firm that didn't join, right, they're not in the industry. They don't incur any costs. They don't incur any revenue, so they're still at zero. Right? They stayed out. Now, if they enter that market, right, we then know that, okay, if the monopoly is setting this higher price, this new firm then enters the market, and they kind of are able to charge a lower price, right? Everyone's going to switch from buying to that existing monopoly more towards the company that sets a slightly lower price. So that new company is going to be getting positive profits, right? The monopolist gets negative profits, right? And this is just in a snapshot, right? The game might be repeated. We're just thinking about if we had just that first period, right? So that new firm enters, undercuts the monopolist's price, pulls away a lot of demand for that monopolist, causing them to have negative profits, and kind of the new firm kind of taking some of what used to be that monopolist profits and making it their own. If the monopolist instead says, okay, I'm actually going to choose a much lower price, so it's not as enticing for firms to enter this market, right? the existing firm, the new firm thinking about entering can either enter or stay out. If they enter at a competitive price, well, they're both charging a lower price. There's now too many firms in this industry, and they both experience negative profits, right? If that firm stays out, well, here, I'm going to assume not just that they're getting close to that competitive price. Let's assume they set that competitive price exactly, right? So that the monopolist is getting zero profits, and then the firm stayed out, so they don't have any cost. So they have zero profits as well. So let's say this is just kind of the payoff structure that we're given. And here we could complicate this, thinking about, I don't just have to set the monopoly or the perfect competitive price. I can kind of start to choose prices in between. But let's just assume for a second we're comparing those two options. So we'll use backward induction and figure out what's optimal for the second person to do. Okay? So let's say we're over here on this side of the decision tree where the monopolist has set a monopoly price. What's optimal, for this firm trying to decide whether or not they should enter? What is it optimal for them to choose to do? Well, if they enter, and the existing firm setting this higher monopoly price, they can get positive profits, which are better than staying out and getting zero. Right? If the monopolist sets kind of a competitive price, what should this firm do? Yeah, they enter, they get negative profits, they stay out, they're zero. Zero is better than a negative value. So we know that here's the two best responses for that person making the decision second, right? The person kind of sequentially choosing second. Okay, then the monopolist looked at this and said, all right, if I set a monopoly price based off of the payoff structure, I know this firm was thinking about deciding to join, will always join, undercut my price, and I'm going to get zero profit, or sorry, not zero, I'm going to get less than zero profits. If I set a more competitive price, or the perfect competitive price, I know that firm would always choose to stay out, and then I'm going to get profits of zero. So the monopolist looks at this and says, well, profits of zero are better than negative profits. So the best response for the monopolist would be to set a competitive price. So here's an example that we see it's kind of natural that helps fight monopoly power, right? Because if there is no barriers to entry and firms can enter that market, then there's always a danger to kind of setting these higher prices and another firm kind of entering and undercutting them, right? So it's kind of like we talked about the oligopolies. It's like, well, I know if they can undercut me, I could undercut them. And we basically get down to where they're charging pretty much the perfect competitive price. In practice, maybe it's a little bit higher, or if the kind of new firm has a different cost structure, right, where their average total costs are higher, maybe I don't have to reduce my price all the way to that perfect competitive point. But these kind of forces would push me to choose a lower than the monopoly price, right? The threat of this firm entry. And not just the threat, but I always know what that firm would do, right? If I'm setting this higher monopoly price, they'll always choose to join, take away some of my profits by undercutting the price. If I set a lower price, I know they're always going to choose to kind of stay out. Yes, keeping my profits lower, but not lower than if I set the high price in the other firm entry. That makes sense how I'm kind of going through. So I'm first figuring out what's the best response or what's the optimal decision for that person choosing second. And then based off, I know what they're going to do. I know these outcomes can't happen anymore, right? Because I know they're never going to choose to stay out or enter under this scenario. So now it's just that first decision maker comparing the only remaining outcomes, right? Or the best, what's best for them of the remaining outcomes, I should say. Questions on this? We'll keep going here. I've got another one. I think so we can kind of think about how would I say what the equilibrium is here. Well, it's going to be that player one chooses to set a competitive price, player two decides to stay out, or firm one, firm two, kind of same as players. So I've got something that I wanted to point out, the difference between these sequential and then kind of these simultaneous decisions. So let's say I've got a simultaneous decision-making game, and it's rock, paper, scissors, right? We're playing rock, paper, scissors. I can think about the different payoffs, right? So if we both throw rock, it's even, we go again. All right, so we'll kind of use that as zero. We didn't win, we didn't lose. All right, well, we get another chance. If the first person throws rock, the second person throws paper, paper beats rock, So player two gets a positive payoff, they win. Player one loses, they get a negative payoff, -1. So we just kind of go through, I mean, if we know the game of rock, paper, scissors, we can write out kind of what all these payoffs would be, right? Anytime they have the exact same choice, they're both 0-0, no one's better off, no one's worse off. Every time kind of we have one beating the other, the person who beat the other person gets a 1, the person who loses gets a -1. So we then want to go through and decide, okay, what's the best responses? Well, now we have twice as many, right? So I say, okay, if player one chooses to throw rock, what's the best response for player two? Well, 0, 1, -1, 1's the highest value, so their best response would be to throw paper. You could then go through all of these. We went through a lot of normal form game stuff last week, so I'm not going to kind of go through every single one. I'm also generally going to keep these at 2 strategies for you, but I want to use this one to prove a point. So we would go through and find out the best responses here. And what we see is there's no Nash equilibrium. There's no combination of strategies here or decisions that leads to them best responding to each other, or no 2 circles in the same way. That's another non-technical way of saying it. Because think about it, anytime like I would see, you know, if I was in the outcome where I threw paper and the other person threw rock, if I could change my decision and they threw rock, I definitely know that I would then choose to, or sorry, if I was the person throwing rock, the other person throws paper, if I'm the person throwing rock, I'm like, well, I'm definitely gonna just change my decision to scissors, right? So there's never gonna be a scenario where we're best responding to each other. We're always gonna be able to kind of change our decision and be better off. So this is just kind of this weird example, this weird game where we know that there's going to be no Nash equilibrium. Simultaneously, this is when we're making decisions simultaneously. What happens if we then move to sequential? Well, the game isn't very interesting. Just intuitively, if you're playing rock, paper, scissors with someone, and they have to throw theirs first, and then you get to decide what to do, who's going to win? Person is only second, right? They're always going to be able to kind of best respond to what that person's doing. So sometimes when we throw in this sequential order of decision making, right, it goes from a scenario where nobody's better off to where you know who's going to win. We can model this, right? So let's say, and I'll kind of draw this out. I think I like this a little bit better, and I'll do this on the board. So I've got player one, go rock, paper, scissors, and then we can kind of think about it as player two has a decision to make in response to each one of these, you know, depending on which choice player one makes. And then they can go rock, paper, scissors, rock, paper, scissors, rock, paper, scissors. Okay. So player one throws, oh, sorry, player one. Player one throws rock, player two throws rock. Outcome is 0-0, rock, paper, right? Then player two wins, player one loses, rock, scissors, player one wins, player two loses. We then go through these. I think I'm just gonna let scissors, or that one was rock, so I just want scissors here, so I don't know what. This out. So paper, rock, so player two is going to win, -1, 1. Both throw paper, 0-0. Paper, player one, player two throws scissors, player two is going to win. Oh, wait, you have this. I have this backwards, don't I? Paper beats rock. There we go. You gotta remember how to play rock, paper, scissors. So player one throws scissors, player two throws rock, player one would lose, player two would win. They both throw scissors, that one's easy, 0-0. Player two throws paper, when player one throws scissors. Player two is going to lose, so their payoff is -1. Player one wins. So what we'll go through is decide what player two's best response is to what player one is doing. So if player one throws rock, what's the best response for player two? 0, 1, -1. 1 is highest, or yeah, they should throw paper. If they see that the other person throws rock, the way they win is if they throw paper. What about here? Player one decides to throw paper, player two would say -1, 0, 1. I'm gonna throw scissors, that's where I win. And then kind of the final one, 1, -1, 0. Well, their optimal strategy is to throw rock. Right? Well, this one's not kind of an interesting one. What's the Nash equilibrium going to be? Well, if I'm player one, I look at this and say, what? I know if I throw rock, player two is definitely going to throw paper, my payoff's a -1. I lose. If I throw paper, I know player two would always use scissors, I'm going to lose. If I play scissors, player two will always use rock, now I'm going to lose. So what we would say here is kind of a unique one. Player one is indifferent between any of those choices because it doesn't matter what they choose, their payoff's always -1. So we actually have 3 Nash equilibrium. We know that we're going to be in one of these outcomes where player two makes the best response to player one and wins, and player one loses. Now we don't know which of those is going to be because player one is going to say, well, all these I'm damned if I do, damned like no matter which one I choose, so I don't even care what I'm going to choose, right? Maybe I'll throw rock, maybe I'll throw paper. It doesn't matter. I know I'm going to lose either way, right? So, it can be that we have multiple. So I think I had this up here as well. Right? We would go through, figure out best response. Player one's payoff's always the same. So we've got multiple Nash equilibria. So just like with simultaneous decision games, sequential decision-making games can also have multiple equilibrium. So here we would say we have multiple Nash equilibrium. And we get a much different outcome if the game was played simultaneously. Simultaneously, there is no equilibrium. Sequentially, there's actually multiple equilibrium, all in which player one loses. Okay. Any questions on that? We're keep moving here. It's starting to make sense how we're kind of solving these, at least the backward induction. With the next one, this is kind of interesting to think about. I'll mention, you might not believe me at first. So just for starting out the example, kind of go with the assumptions that I'm making, and then we'll talk about maybe in practice what this looks like. So people have done this. It usually maybe has a better effect if I had $100. Well, if I had a bunch of $101 bills and I gave it to one of you and then said, okay, here's $100. You have the option to share with a person next to you. Right? You can give them $1, you can keep 99. You can give them 50, you keep 50, any increment of 1. Right? So you've got all these dollars, you're trying to figure out how many to give the other person. Now the catch is you only get to keep that money if the other person accepts your offer. Right? So if you offer them $1 and they reject that, you get 0. You keep nothing. Right? So that's kind of the game. So we can start to think about the decision-making process. The first one is someone offers, right? $0, $1, $2, $3, $4, all the way up to 99 to the other person. Right? So we'll start out kind of thinking about here's player one. They can be very selfish. Give $0 to the other person. They can give $1 to the other person. They can give $2. You can imagine we could go off for all the way to giving them 100. Right? But we don't have to. I can kind of make the point with just a couple of these. Okay? So if player one offers the other person $1, so here we're now thinking about the second person is making their decision. Right? Here's player one's strategies. Now player two is going to have their own strategies. So what did I say player two gets to do? Well, they either decide to accept or reject these offers, right? So we can kind of think, I'm just going to use A and R. If you really want to, you could write out the whole word, accept, reject. I'm just going to shorthand it here. Right? That's their decision, no matter how much the other person offers them. They can always decide to accept or reject. Yeah.
Do they know how much player one gets?
Yeah, so they know this, right? They know that player one has $100 and they know that player one's deciding how much to give them. Right? So we'll think about the payoffs. So if player one offers the other person $0, and let's just say they accept, right? The payoff to player one will be 100, payout to player 2 is 0. If they reject it, how much do each people get? 0. In fact, we can just go ahead and fill out all these rejects, right? If they reject, nobody gets any of the money. So we always have these 0, 0 outcomes. If I offer the person $1 and they accept, 99 would be how much player 1 keeps. Player 2 gets $1. 98 for player 1, $2 for player 2. And I could like go through and do that all the way down to, offering them $100 if I wanted to. Well, here is where it's kind of interesting. This is where we'll talk about the theoretical prediction of this game and then what happens in application. So if I'm looking at player 2, right? I've got a backwards induct, right? I'll use backwards induction here. So for player 2, if player 1 offers them $2, what's their best response? Yeah, having $2 in my pocket's better than 0. What if they offer me 1? Yeah, if I just care about money, right, I'm going to take the $1. Now here, they're indifferent, right? So I don't know what they're going to do there, right? It's a little risky. They could accept, they could reject. All they care about is money. They're indifferent between those two choices, right? $0, $0. So then what's player 1 going to do, right? Player 1 looks at these best responses and says, well, if I offer 0, I know it's possible that I'll get 0 instead of 100, right? I don't know which one of these I'm going to end up in, right? And so I can think about it as the payoff here would be 0, right? I know that it's possible I end up down here and I get this payoff of 0, right? I'm going to use this to indicate what their best response is. So I just highlight it in a second. If I'm looking at how much I get if I offer them $1, I know for sure I'll get 99, right? And then if I offer them 2, I know for sure I'll get 98. So if I'm looking at this, if I offer them 0, there's a chance I get 0. If I offer them 1, I know for sure I'm getting 99. If I offer them 2, I know for sure I'm getting 98. So here, what's the best response for player 1? 98, lower than 99, is higher than 0. So I know that they're just going to offer $1. Now, an easier way to set this up is to think about if 0 wasn't an option. Well, then you can think about it. It's always going to be best for the second person to just accept whatever I'm willing to give them. So I'll give them the smallest possible amount. Right? So the Nash equilibrium here would be, we have 2 circles in the same one. We know that player 1 is always going to choose to offer $1. If all they care about is money, player 2 is definitely going to accept. Okay? So we kind of have, if I have to offer you an amount different than 0, this complicates it a little bit. But really, you could think about like we have to use some expected value here. If this person equally is likely to choose either one, well, I could get 0 with a 50% chance, 100 with a 50% chance. So my expected payout is 50. If you've done like, I probably haven't taken finance classes yet, but we can kind of shut that down and say they at least have to offer $1 minimum. Well, if they have to offer $1 minimum, they're always going to choose to just offer that $1. Right? It's always going to be the best response for player 1 to what player 2 will do. Any questions or concerns with this? Why might this not work?
Because people are greedy.
So people are greedy, right? That's what this shows. If all people care about is money, then what is player 1 always going to offer the other person? Just $1. So if that person says, well, $1 is better than 0, then we're going to end up here, right? But how might we end up with that second person rejecting that offer? The other person's greedy. Maybe I want to be vindictive or spiteful, right? And so if we have anything other than money that might bring me joy, right? If I value this person who just tried to offer me $1 and I know they could have offered me 50 and had to be an even split, well, maybe I value the vindictiveness or the spitefulness more than $1. Right? I'd pay a lot more than $1 to see that person get nothing. Right? So in practice, these models become a little more complicated. These payoffs are a little harder to figure out because you're not just trying to figure out the monetary payoff. You're trying to figure out, well, what are these additional benefits to making these decisions. And if I factor in human behavior like spitefulness, maybe I have a real strong pull for equality, right? So sorry, before I do that one, here, the spitefulness one kind of makes sense, right? You can imagine how like, okay, yeah, I get it to keep $1, but if I rejected seeing that other person lose $10, I'd pay up to $10. Or sorry, see the other person lose 99, I'd pay $10 to do that, right? Because they're being such a jerk to me. I want to see them kind of also have a bad outcome. So I value that really high, right? Well, now you can kind of see here. I know if there is some spitefulness in the other person. Well, now player one looks at this and says, well, I know if I offer this, it's way too insulting, right? Which then means the other person's going to reject it, right? So if you were trying to make, so maybe instead you go to the next one, right? Oh, well, offer a little bit higher amount. Yeah, I get to keep less, but I know they're going to reject it. So I actually would only get 0 if I offer them $1. So maybe I offer them 2, right? But maybe they're really spiteful there. They still feel like you're offering a really low amount and they'd still pay $10, right? So you can kind of imagine there's a point where you offer them a value high enough where they don't feel like you're insulting them, right? And they don't feel like they would pay as much to be spiteful back towards you, right? So they've done this experiment. I don't think they did it with $100, but I think they did it with 20 and allowed for multiples of 50 cents maybe or a quarter. And what they found was that you need about 20% of whatever, I think they played around with a different prize amount too, like $10, $2, or sorry, $10, $20. And what they found was you need to offer about 20% of whatever that pot is for the other person to not be like really spiteful and just reject it. All right. So you can think about this as, if I know you've got $100, right, and you're offering me amounts 0, 1, 2, 3, you weren't even trying to be fair. And so I'm very spiteful. If you only offer me 20, well, I understand. You have the decision. You were given the money first. I get how you might be a little greedy. You're at least trying to give me something, right? And so they found in practice it was around like that 20% mark. So if you did give them $100, once you start to offer the person about 20, then in practice it actually starts to get accepted, right? Because you don't have this kind of added benefit from the other person of being spiteful, overcompensate the dollar amount they were actually given. So, long story short, in practice, the behavioral aspect just complicates figuring out what these payoffs are. But once we knew these payoffs, we would still go through and solve the models the same way. Okay. Another thing that can get added in when you do something like this is maybe, let's assume for a second that the other person isn't spiteful at all, right? So we start out thinking about, here's these different amounts we can offer. The other person isn't spiteful at all, right? So I know they're always going to accept my offer, right? Because they have no malice in their heart, right? $2 is better than 0. $1 is better than 0. They were always going to be kind of accepted. If the other person, though, has built into their psyche that they value equality, right? So if they value equality, these outcomes where they're getting to keep way more than the other person, they feel really guilty about that, right? And so there's some negative cost, right? There's some additional cost to that. So yeah, they're getting to keep $99, but man, maybe this really weighs on their conscience and actually feels like, I'd pay $200 to get rid of this feeling. So the actual payoff to them feels negative because they feel so guilty about, just offering this person $1 out of the 100, right? So now it may not be that extreme, but I'm using that extreme of a number to kind of make a point where it just starts altering the payoffs, right? If I value equality, then I may not, even if I know the other person is going to accept, I might want to offer a higher amount, right? Because then I don't feel this guilt, right? And I think one of the things that came out in the studies was there was some people, this was not true about the average, but there was some people that no matter how large the prize pool was, no matter what increment they could offer, they always chose to offer a 50-50 split, right? And so they kind of identified these people as having a very high value for equality. And that anytime they offered an amount that wasn't a 50-50 split, they felt so guilty about it, like they were cheating out the other person, that they wouldn't make that choice, right? The payoff actually felt like it was negative in those situations. So once again, we can still solve those models. It just makes the payoffs harder to figure out. Because you can't really ask someone like, I mean, you can, there are ways to do it, but it's hard to think about how do I really figure out how much somebody would be willing to pay for spite? How much would be someone willing to pay for equality? Now, with these things called economic experiments, like where they give actual people money to, and then kind of record the interactions, you can back out what those valuations are. Like I said, it looks like for spitefulness, it's about 20%, right? That you have to give it. So I don't know, kind of an interesting example. Also, just like I want to start bringing things up, we're talking about these models, and we can solve these models. It's just I'm giving you payoffs. In practice, these payoffs might be a lot harder to figure out. Okay. Any questions there before we keep on? Okay, so on Friday, we'll revisit some of this. We'll work through a couple additional examples. We'll go back to thinking about simultaneous and sequential decisions. But I want to introduce the next topic that we'll start talking about today, go through it a little bit, which is externalities. Okay. So we'll start thinking about externalities in several directions, or in both directions, positive and negative. So all an externality is an additional cost or an additional benefit to somebody outside of the market. So the easiest type of externality to think about is, let's say you don't, let's say you don't consume, you're vegan, you don't consume meat at all, right? There are people who produce and consume meat products, right? Their decision to consume and produce meat products might have additional costs on the people nearby. So if my house, I'm a vegan, but I live next to a hog farm, there's a huge negative externality, right? Like I have to smell that. I don't know if any of you grew up anywhere near a hog farm. I had one like half a mile down from my house, and if the wind's blowing right, it's unbearable, right? And so there's a huge additional cost to someone outside that market. If they're a vegan, they don't even consume the meat. They're not a producer, they're not a consumer, but they're incurring a cost, right? So by this market operating, somebody else is bearing this cost. The other easy one you can think about, pollution, right? Any type of production process that's creating air pollution, people who aren't producers or consumers of that product still have this additional cost of air pollution, right? So negative externalities, I think, are really easy to think about. Positive externalities may be a little bit harder. So I think my favorite, I don't know. Oh, I guess a somewhat relevant one, if you think about, our immunizations, right? So there's a longer discussion there, but let's assume you have an immunization, right, that completely stops the spread of a disease, right? Then you getting that immunization benefits everybody else that comes in contact with you, right? Because you can't give that disease to them. So there's positive externalities to you purchasing that vaccine. Other people who didn't decide to get one or not are still benefiting from your choice. Or the other one that's a really good example of a positive externality, you think about education, right? You chose to come get a college degree, right? The university is paying these costs, they're paying professors, they're building these huge buildings. Also, this is an aside. I had this discussion with somebody, I just keep saying, how many Starbucks are there on campus? Are there 3 or 2? Just 2, okay. I just saw the one down on the north side of it. I was like, isn't there one? And then there's the coffee place in the library. I was like, how much caffeine do you need? But anyway, they spend all these costs to produce, right, the possibility for you to get a degree. You're all consuming, right, their product, which is their degree. So you know, producers and consumers of education, but who benefits from you having a higher degree, right? Well, you're going to go out in the world, you're going to be a much more productive member of society, fingers crossed, right? You're going to help invent new products. You might, revolutionize a certain industry that's going to then have benefits for lots of people. So your education has additional benefits to people who weren't involved with you getting the education at all. Right? So we've got positive, we've got negative externalities. We can start to think about, well, if those additional costs gets too high, like maybe there's some surplus in the market for, I don't know, coal-powered energy, right? There are consumers and producers of it. They both gain from the consumption and production. But if the cost of society in terms of pollution becomes too high, we may not want as much coal-powered electricity, right? Or we might want to find ways to kind of reduce that pollution, right? That negative externality. So these additional costs, these additional benefits will skew what the optimal point is, or the equilibrium for society. Right? The market itself will arrive at an equilibrium, but for society as a whole, the equilibrium might be a different quantity price combination. Where's some other ones here? So you can think of, I don't know, this one's pretty rare, but positive production externalities. I think the best example, I really like the bee example there, right? If you got like a, I don't know, it's not a bee farm. I don't know, what do they call it? Well, you really have got those boxes and beehive. Yeah, but you've got lots of beehives. I don't know. Is it a bee farm? I don't know what it is, but yeah. So, someone who's doing that, a beekeeper doing it, right? If I've got, some type of crop nearby, right? Some type of flower producing crop, I benefit from having those bees in the area, right? Because they help keep my crops pollinated, right? Or at least that process going. So there's a positive production externality. Someone else producing honey with their beehives is benefiting me kind of with like an apple orchard, whatever the fruit is, right? Some flower kind of agriculture product, right? And then the other one I did not mention, what did we say? We did pollution. Sometimes there are negative consumption externalities as well. So I gave you kind of negative production externalities in terms of thinking about pollution or like hog farms, but also negative consumption externalities. To me, like the easiest one is smoking. Like if somebody is deciding to consume a cigarette next to me, I mean, it's all personal preference, but it is a huge negative cost, or a huge cost to me. I hate the smell of smoke. I'm not a big fan. So, but yeah, these are ideas, right? We can have negative and positive externalities either from consumption or production. Okay? So, think about what this is going to look like. And I think instead of the slides here, I'll just make it one more. So, let's say, I think I did gasoline here. And we'll just think that the process of gasoline produces negative production externalities. That as these companies are producing more and more oil, more and more gas, they're polluting the environment. Okay? So this is how we'll generally think about this is, here's our supply and demand for gasoline, okay? We said that demand represents the marginal benefits of the consumers of that product. Supply represents the marginal costs of the producers of that product. Okay? So we said, okay, we know the market is going to arrive. I'm trying to call this, we'll assume it's like a perfectly competitive market at this price and quantity. This is PC, sorry, it's perfectly competitive. What's going to happen if the production of gasoline or oil has these huge costs to society from air pollution? So people who aren't even, maybe people driving Teslas, right? They're not even involved in this market. They have to bear this cost of the fact that the air is not more polluted. So at every single unit produced, the cost to society, or what we'll call the marginal social costs, will be whatever the marginal costs are to the producers, but plus this kind of external cost to people not even involved in that market. Every unit of oil or gasoline that's produced, or barrel, however you want to measure it, is producing some cost in terms of air pollution to people not even involved in that market. So at every single quantity, it's almost like my marginal social cost, right? The cost to everybody, not just the people in this market, is going to be higher. And that's going to be true at every single quantity, right? Because for every barrel of oil produced, that's, I don't know, however many, I don't know, nanometer, however they measure the pollution levels in the air, all right? So as I produce more, I am just increasing the kind of negative externalities. So I can think about, it's almost like with negative externalities for society, the supply curve is actually a little bit lower. Sorry, not lower. It's shifted to the left, right? So the supply curve or the costs are a little bit higher. So at every single quantity, there's an additional cost, so that marginal social cost curve will be above wherever that supply curve is that reflects just the company's costs, right? Because the companies don't necessarily care about the air pollution, and, they don't have to pay to deal with it, right? They don't care that the people around their factories maybe are getting this reduced air quality, having this cost of their life. And that might be a pessimistic way of looking at it. But we're starting out assuming that these companies have just profit maximizing. They just care about increasing profits. So where would the optimal point be for society here? Well, there's this additional cost of production. We'll figure out where does the marginal social cost hit the marginal benefit. Okay? Because if you think about for these units here, the additional costs were above the additional benefits. So society was actually losing out, right? For every quantity past this point, the marginal social costs were above the marginal benefits. Now here, it makes it easier also, we're assuming there's no positive externalities, so the marginal benefits just reflect society's benefits. There's no external benefits here, just external costs. We'll kind of talk about later in the week if we have the combination of the two. So if we kind of go past this quantity, the benefits to society are lower than the costs. So why would I keep producing that much? So the optimal point for society will be, I call this the socially kind of efficient quantity or social equilibrium quantity. And then if we were able to set the price for society's optimal point, it should be a little bit higher. So if there's these additional costs like pollution, what's actually better for society is actually to have a little bit less produced, right? Lower quantities of oil because that's less produced, less pollution for society. And then as a result, kind of the unit provided in the market, we'll see that the optimum price should be a little bit higher for that product as well. And that's because the market isn't factoring in these external costs, right? The market is black lines, right? So it's the company's marginal cost and the consumer's marginal benefit. But for society, it's not just the company's marginal cost, it's the company's marginal cost plus all these additional costs from pollution that these people that just are not even involved in this market might be experiencing. So we'll walk through, we'll kind of go through more of these negative externalities and talk a little bit more about them. How do we maybe resolve this? How do we end up at that socially optimal point? With the positive externalities. And then, like I said, I'll probably continue that into Friday and then go through some of those practice problems on Friday again. Okay. All right. So before everybody gets out of here, so you all showed up. I'm just going to turn the eye clicker on. Just respond with something on your way out. And you'll get 10 out of 10 for kind of being here, participating, listening today. Oops. Give me 1 second. All right, there you go. All right, I'll see you guys on Wednesday.
Says no base.